Hello everybody, this is the outline of my talk. First I will discuss the motivation of our project, which is disabling electronic devices, and then I will talk about the destruction approach via on-chip release of corrosive chemical agent. Next, this will be followed by the fabrication process, the sealing methods, experimental results, and the conclusion. In every case of theft, capture, or loss of electronic device or system, there is a ubiquitous fear of important information landing in the hands of unwanted subjects. This is particularly important in cases of mission-critical military operations and financial transaction applications. In these cases, it becomes absolutely imperative to incorporate a disabling mechanism to destroy the hardware and the information before any information is obtained by illicit means. There are several disabling mechanisms that are used to ensure that significant information is not compromised from stolen or lost hardware. The utilization of access password and encryption is generally used as the first line of defense, but with sufficient effort, eventually encryption can be cracked. Hence, in addition to software encryption, hardware itself can be directly disabled. Hardware disabling techniques include the use of energetic layers that melt and explode, thus destroying the target hardware. One such example will be shown in Shashank Shekhar Pandey's poster on Wednesday afternoon. A second disabling mechanism can be triggered chemical attack, which will etch and hence destroy the hardware. In this paper, we will focus on this methodology. We will fabricate a chip that will release a corrosive chemical agent that will etch the target chip under electrical control. On this slide, there is a schematic which shows the cross-section of the triggered chemical release device. There is a 70 micron thick reservoir with thick polymeric walls storing a corrosive chemical agent. The device also includes a triggering mechanism that will release the chemical compound under electrical control. This device can be bonded or fabricated on top of the target electronic chip, which has to be disabled on demand. When the trigger is activated, the electronic chip is exposed to chemical attack from the released chemical compound, and hence after a few seconds it will be destroyed permanently. This slide shows how the microfluidic reservoir and the triggers are implemented. The polymeric device consists of an array of segmented reservoirs and embedded heaters. The reservoirs are filled with a corrosive agent. In this case, it is a dilute solution of hydrofluoric acid, and subsequently sealed. The device is activated when the bottom wall of the reservoir is melted by the heater, releasing the corrosive agent. To test all these ideas, we fabricated a test chip. It consists of a substrate wafer, which can be either glass or silicon, with titanium test resistors patterned at the surface. The titanium test resistors are indicators of the chemical attack on the chip. On this test substrate, we fabricate the microfluidic plane. The bottom wall of the reservoir consists of a layer of perylene and embedded aluminum heaters. The reservoir is filled with 100 to 1000:1 a dilute solution of VHF, which etches both the silicon dioxide passivation layer and the metal lines. Finally, the reservoir is sealed by a layer of SU8 and perylene. This slide shows the fabrication process of our test device. The fabrication starts with bare glass wafer or a silicon wafer with 0.5 micron of silicon dioxide passivation. 0.2 micron thick titanium test resistors are next patterned on the surface. Next, we build the bottom wall of the reservoir with embedded heaters. This is done by first depositing a 0.5 micron layer of perylene and then evaporating and patterning 0.5 micron of aluminum to define the heaters. The aluminum heaters are next coated by another 0.5 micron layer of perylene. Next, we fabricate the hollow cavities of the reservoir by sacrificial etch technique using 16 micron thick layer of photoresist as a sacrificial layer. Next, we fabricate the top wall of the reservoir by depositing a 5 micron thick layer of perylene. Holes are etched on the top wall to the spacer layer by oxygen plasma, and then the entire device is dipped in acetone overnight to remove all the spacer, leaving behind the hollow cavities. Next, the cavities are filled with a dilute solution of buffered hydrofluoric acid and subsequently sealed. This slide in details discusses about the cavity filling and sealing process. First, the sample with released hollow cavities are dipped into a bath of BHF. Next, they are pulled out of the bath and immediately flash frozen by placing it on a liquid nitrogen cooled metal chuck. This freezes the BHF inside the reservoir and also leaves a thin film of frozen BHF on the surface of the reservoir. The frozen BHF on the top surface of the reservoir can be removed by air drying using an air gun for about 1 minute. This leaves the top surface cold but dry. Next, we spin coat a 50 micron thick layer of SU8 photoresist and then immediately expose it to UV radiation to harden it. This procedure completely seals the frozen BHF inside the reservoir cavity. Then a final layer of perylene is deposited to encapsulate the entire device. This is an optical photo of the test chip built on glass substrate wafer. We fabricated this test chip on glass wafer to determine the minimum energy required to release the BHF. We also fabricated similar devices on silicon substrate. These photos show the cross-section of the reservoir. On the picture on the left, we can see the support pillars which prevent the top wall of the reservoir from collapsing. While in the picture on the right, we can see the micro heaters embedded in the bottom wall of the released cavity. The volume of the chemical agent that the reservoirs can contain is approximately 1.6 microliter per centimeter square. This photograph shows the partial refill of the cavity with BHF when the sample was quickly pulled out of the bath, showing the presence of bubbles. These bubbles can be removed if the sample is immersed in the bath for about 2 hours. After the samples are pulled out of the bath, they are flash frozen and air dried. These pictures show 2 important stages during the freezing process of the sample. The picture on the left shows frozen BHF after flash freezing and air drying, while on the right we see frozen BHF after spinning and exposing of SU8. Our test device was subjected to 2 types of electrical tests with the setups shown below. To detect the chemical attack on the chip, the resistance of the titanium test resistor was monitored by connecting it to a series 100 kilo ohm resistor and a 15 volt DC power supply. The nominal test resistance of the resistor was 60 kilo ohm. The voltage across the test resistor was monitored using a digital storage oscilloscope. In the constant power electrical setup, the aluminum heater was directly connected to a DC power supply, while in the constant energy setup, first a capacitor was charged to a fixed voltage V. Then switch 2 was open and switch 1 was closed, and we discharged the capacitor onto the aluminum heater. This video shows the melting of perylene at different heater voltages. The video has been accelerated 4-fold. In the constant power burst test, a DC power supply was directly connected to the aluminum heater, and the damage on the chip was monitored using a video camera. The perylene melted at different voltage, and these pictures show the melting of perylene at different applied heater powers. The melting of perylene starts at about 20 watts, and by the time we reach 30 watts, almost all the perylene of the bottom wall melts. But though this process also bursts open the chamber, this is a very inefficient method of actuation, as a huge amount of power gets dissipated to the substrate wafer without contributing to the wall melting. We can actually calculate the amount of energy required to melt the paralleling wall. The two components to the energy needed. First is the heat capacity of the polymer wall and the heater from room temperature to the melting temperature parallel, which is about 290 degrees Celsius. And the second component is the latent heat of melting of parallel. We calculate the exact amount of energy considering the dimensions of the reservoir, which turned out to be 41 millijoule per centimeter square. We can also experimentally measure the melting energy using energy discharge burst test. In this experiment, we charge a 0.47 microfarad capacitor with a voltage V and then discharge the capacitor onto the heater. The minimum melting energy is equal to that energy which produces substantial visual damage onto the sample. The minimum, when we conducted this experiment on a glass chip wafer, then the minimum energy turned out to be 35 millijoule per centimeter square, which is in rough agreement with our calculated value. This slide shows the plot of test resistance versus time when the device was activated. We can see that the test resistance rises from about 60 kilo ohm to a very high value in about 10 seconds, showing that the test resistor got etched by the released DHF. In conclusion, we fabricated a polymeric device that could store and when triggered release a corrosive chemical agent that could destroy the target electronic chip below. The minimum activation energy of our device turned out to be 35 millijoule per centimeter square. In about 10 seconds, the test resistors got completely etched. We built this device on silicon or glass wafer, but we could also bond this device on an existing electronic chip to incorporate the triggering mechanism to any off-the-shelf existing microchip. Thank you.